On July 1, 2025, astronomers discovered a fast-moving blur streaking through the solar system, an object later confirmed by Mars rover imagery and calculations to be the third true interstellar visitor. But just as routines formed around cataloging distant wanderers, Harvard's Avi Loeb threw the scientific world into chaos. Based on 7 unexplained anomalies, he now claims there's a 40% chance this is not a comet at all, but a disguised alien spaceship, a Trojan horse on a trajectory past Mars, Venus, and Jupiter. If he's right, humanity must prepare for the worst. What are these anomalies and what exactly is hiding inside 3/Atlas? On July 1, 2025, the Atlas survey in Chile registered a faint, fast-moving blur against the backdrop of deep space. The automated detection pipeline flagged the object for its unusual velocity and direction, prompting immediate follow-up from ground-based telescopes. Within hours, astronomers confirmed its hyperbolic trajectory, evidence it was not bound to the Sun, but visiting from interstellar space. The object was cataloged as 3I/Atlas, marking only the third time such a visitor had been tracked entering the solar system. The initial confirmation relied on a chain of technical checks. Atlas's twin 0.5-meter telescopes captured the object in a series of 30-second exposures, each frame showing a dim speck inching across the star field. Automated astrometry routines calculated its position, velocity, and acceleration, ruling out orbital ties to any known solar system body. The Minor Planet Center logged the detection, and observatories in Hawaii and South Africa quickly added their own measurements. By July 2nd, the International Astronomical Union issued an official circular. 3/Atlas was real, and it was moving fast. As the object's path carried it toward Mars, astronomers searched for opportunities to observe it from other vantage points. The European Space Agency's ExoMars Trace Gas Orbiter, circling the red planet, was tasked with an ambitious imaging campaign. On October 3rd, during 3D/Atlas's closest approach to Mars, about 30 million kilometers away, ExoMars's CASIS camera began a sequence of 5-second exposures. The challenge was immense. The object was up to 100,000 times fainter than the Martian surface targets the instrument was designed to study. Each frame captured only a barely perceptible glow, but by stacking 20 exposures, mission engineers produced a composite image. The result showed a fuzzy white dot, evidence of a nucleus surrounded by a faint coma, drifting slowly across the field. The data from ExoMars provided the first independent, space-based confirmation of 3/Atlas's existence and trajectory. While the nucleus itself could not be resolved, the stacked images revealed a diffuse envelope of material, consistent with, but not definitive for, cometary activity. The European Space Agency released a processed animation on October 7th, highlighting the technical feat and the significance of the detection. Meanwhile, Mars Express attempted its own observations using the HRSC camera, but its shorter exposure times and lower sensitivity meant the object remained invisible in individual frames. Scientists continued to process stacked data in hopes of recovering a signal. No images or confirmation came from NASA's Perseverance rover or other U.S. assets, as the ongoing government shutdown limited communication and operations. The only verified visual evidence from Mars orbit came from ESA's ExoMars orbiter. With the object's position and movement now firmly established, researchers turned their attention to the anomalies in its behavior, anomalies that would soon spark debate about its true nature. Only in the last decade have astronomers confirmed the existence of interstellar objects passing through our solar system. The first, 1I/Oumuamua, was discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua's visit lasted just a few weeks, but its odd shape, rapid rotation, and unexplained acceleration led to intense debate. Unlike anything seen before, it showed no typical signs of cometary activity, no tail, no outgassing, leaving its true nature unresolved. Some argued it was a fragment of another solar system, while others, including Avi Loeb, suggested it could be artificial in origin. 2 years later, in August 2019, a second visitor, 2I/Borisov, entered the record books. This time, the object behaved much more like a textbook comet. Observatories around the world watched as Borisov developed a classic tail in coma, shedding gas and dust as it swept past the sun. Spectroscopy revealed water, carbon monoxide, and cyanide, compounds familiar from comets born in our own solar system. The evidence pointed strongly to a natural origin, and Borisov was quickly accepted as a standard interstellar comet, albeit one that confirmed such objects are not as rare as once thought. The arrival of 3I/Atlas in 2025 stands out not just for being the third of its kind, but for the questions it raises about what counts as typical among these cosmic visitors. In less than a decade, the catalog of interstellar objects has grown from 0 to 3, but each has challenged expectations in a different way. Oumuamua's brief, enigmatic appearance hinted at the possibility of entirely new classes of objects, or even technology. Borisov, with its familiar cometary features, offered a reassuring counterpoint, suggesting that most interstellar wanderers might simply be icy leftovers from distant planetary systems. But 3I/Atlas defies easy classification. Its estimated speed, about 60 kilometers per second as it passed Mars, puts it among the fastest objects ever tracked in the inner solar system. Its size, at over 5 kilometers across, dwarfs both Oumuamua and Borisov, making it the largest interstellar object detected so far. The odds of seeing 3 such objects within a single decade remain low, especially given centuries of prior astronomical surveys that found none. This sudden increase suggests either a stroke of observational luck or a new era in which powerful surveys and space-based telescopes are finally catching what once slipped by unnoticed. The rarity of these events has shifted scientific priorities. Every new interstellar object is now treated as a potential window into the unknown, an opportunity to test theories about the formation and evolution of planetary systems beyond our own. By comparing the properties and behaviors of Oumuamua, Borisov, and now 3I/Atlas, astronomers are building a baseline for what is possible and what might be considered truly extraordinary. With each discovery, the line between the familiar and the unprecedented grows sharper, setting the stage for deeper investigation into the mysteries that 3I/Atlas presents. Spectroscopic campaigns targeting 3I/Atlas began as soon as its interstellar origin was confirmed. The James Webb Space Telescope was among the first to secure time on its near-infrared spectrograph, followed by ultraviolet sweeps from the Swift Observatory and high-resolution polarimetry from the Very Large Telescope in Chile. Each instrument, designed to reveal the chemical and physical properties of comets, returned data that stood apart from expectations. The most immediate surprise came from the ratio of carbon dioxide to water vapor in the coma. Standard comet models predict water as the dominant volatile, especially for objects heated by the sun for the first time. Instead, Webb's spectra showed a carbon dioxide to water ratio of nearly 8:1. This is an order of magnitude higher than values recorded for either 1I/Oumuamua or 2I/Borisov, and far beyond the typical range for comets in our own solar system. The result suggests a composition dominated by carbon dioxide ice, with water playing a minor role, an inversion of the usual pattern. Ultraviolet observations with Swift targeted the hydroxyl emission, a direct tracer of water outgassing. Even after stacking exposures, the hydroxyl signal remained weak, barely above the noise floor. This absence of strong ultraviolet emission further supported the notion that water was scarce in the surrounding cloud. For planetary scientists, the lack of water vapor was not just unexpected, it was almost unprecedented for a body presumed to be a comet. Polarimetric measurements from the Very Large Telescope added another layer of complexity. At a phase angle of 7 degrees, the light scattered by 3I/Atlas showed a linear polarization of -2.77%. Negative polarization at small angles is not unusual for comets, but the magnitude here was extreme, falling outside the range established by decades of cometary surveys. Such a strong signal implies that the dust grains in the coma are either unusually small, highly reflective, or composed of exotic material. Some researchers pointed to the possibility of metallic particles, echoing early hints of nickel lines in the spectrum. The combined dataset painted a picture at odds with the standard comet paradigm. Instead of a water-rich dusty nucleus, 3I/Atlas appeared to be dominated by carbon dioxide, with a faint or absent water signature and a dust envelope with unusual polarimetric properties. Each anomaly, taken alone, might be explained as an outlier or an artifact of observation. Together, they forced astronomers to reconsider the boundaries of what constitutes a comet, and whether 3D/Atlas fits that definition at all. These findings set the stage for a broader reckoning with the object's full list of anomalies and the growing scientific debate over its true nature. The European Space Agency's release of the CASIS animation on October 7th drew immediate attention, but the data behind that GIF remained out of reach. The animation, stitched from 25-second exposures, showed 3I/Atlas as a faint, drifting blur, proof of a successful detection, but not a source for deeper analysis. Nick Thomas, principal investigator for the CASIS camera, described the effort as one of the most challenging in the instrument's history. The object, he explained, was tens of thousands of times dimmer than the Martian landscapes CASIS was built to survey. Even with careful timing and image stacking, the result was little more than a fuzzy white dot surrounded by a ghostly haze. Mars Express, operating with a different camera system, faced its own limits. The high-resolution stereo camera could only manage half-second exposures, far too short to pick up the faint glow of an interstellar visitor at such distance. Colin Wilson, project scientist for both Mars Express and ExoMars, acknowledged the technical constraints and said the team was still analyzing stacked data in hopes of teasing out a signal. As of October 9th, no images from Mars Express had been released. The mission's scientists remained in wait-and-see mode, sifting through faint traces for any sign of the object. The absence of NASA imagery only deepened the uncertainty. The U.S. government shutdown had brought routine science operations and public communications to a halt. No word came from Perseverance, Mars Reconnaissance Orbiter, or any other NASA asset. Researchers searching the Mars 2020's PDS archive found no trace of 3I/Atlas in the image catalogs, no exposure logs, no press statements. For some, the silence was a simple bureaucratic artifact. For others, it was a source of mounting suspicion. Into this vacuum, speculation rushed in. Social media forums and fringe communities began to fill the gaps left by official silence. Remote viewing message boards lit up with sketches and visions of luminous cylinders and artificial lights. Bertie Dworsky, a well-known figure in these circles, posted a series of predictions about the object's behavior, claiming to see structures in the CASIS GIF that others dismissed as compression artifacts. Debates raged over whether the faint anti-tail seen in the animation was a camera artifact or evidence of propulsion. Some insisted that the lack of a clear cometary tail, combined with the object's precise alignment with planetary orbits, proved deliberate intent. The contrast between the European Space Agency's openness and NASA's enforced quiet fueled more than just curiosity. Nick Thomas's public statements, describing the technical hurdles and the limits of the data, were dissected for hidden meaning. Colin Wilson's cautious optimism about future analysis was interpreted as either scientific prudence or a coded warning. The absence of raw image stacks and exposure logs from both Mars orbiters left even mainstream astronomers unable to verify details or run independent analyses. Every gap in the record became a breeding ground for alternative theories, from benign neglect to active cover-up. With the public and scientific community both grasping for answers, the urgency for decisive evidence grew sharper. The next phase of analysis would have to proceed with what little data was available, knowing that the story of 3I/Atlas was already slipping beyond the control of official channels. Avi Loeb's analysis draws together a set of features that, in combination, stretch the limits of natural explanations. The first is sheer scale. Atlas measures more than 5 kilometers across, with a mass estimated at 33 billion tons. This makes it not just large by comet standards, but an outlier among all known interstellar objects. Its speed, about 60,000 kilometers per second, compounds the puzzle, since such velocity is rarely seen for bodies of this size entering the solar system. Trajectory offers another layer of improbability. 3 Atlas moves within 5 degrees of the ecliptic, the plane where the major planets orbit. Calculations show a 0.2% chance for this alignment to happen by accident. Even more unlikely, its path brings it close to Mars, Venus, and Jupiter, with the odds of this triple encounter dropping to just 5 in 100,000. Loeb notes that this isn't just a statistical fluke, it's a pattern that invites scrutiny. Chemical analysis deepens the mystery. The plume surrounding 3I Atlas is rich in nickel, with far less iron than expected. This composition is unusual even among rare metallic asteroids and more closely resembles industrial alloys than natural cosmic debris. On top of that, the object's light shows extreme negative polarization, a property not typical for known comets, suggesting either engineered surfaces or unfamiliar dust structures. Visual evidence challenges the comet hypothesis. Early images showed no classic tail, but rather a faint anti-tail, an elongated streak pointing forward, not behind. Later images revealed only a small tail, inconsistent with the expected outgassing from a body this size and speed. The vector of its arrival, as Loeb points out, matches the direction of the famous "wow" signal detected in 1977, a coincidence that further fuels debate. Loeb assigns a probability as high as 40% that 3I Atlas is not entirely natural, rating it a 4 on his own scale for potential technological origin. Each anomaly, taken alone, might be dismissed as noise. Together, they form a case that demands urgent and rigorous testing, as the scientific dilemma moves from curiosity to potential consequence. As 3I/Atlas speeds toward its closest approach to the Sun, the next few weeks will define what science can and cannot say about its origin. On October 29th, the object will reach perihelion, traveling at nearly 68 kilometers per second. This window offers a rare chance to observe changes in its activity, brightness, and structure under intense solar heating. Astronomers have outlined a checklist of critical observables: the development of a classic cometary tail, shifts in outgassing rates, and any sudden alterations in trajectory or spin. Each of these markers can help separate natural cometary behavior from more exotic possibilities. The speed forecast is especially important. At nearly 68 kilometers per second, 3I/Atlas is moving faster than most solar system comets, making detailed tracking a technical challenge. Instruments on Mars orbiters and ground-based telescopes will be pushed to their limits to catch any fleeting signs of activity. The hope is that as perihelion approaches, increased sunlight will trigger clear, measurable changes, whether in the form of a growing tail, enhanced gas emissions, or new spectral fingerprints. Meanwhile, attention has turned to the European Space Agency's Jupiter Icy Moons Explorer, or JUICE. While not designed for this target, mission planners are evaluating whether its instruments might capture supplementary data. As 3I/Atlas passes through the inner solar system, even a single image or spectrum could provide valuable evidence, especially if it reveals features that ground-based observatories cannot detect. The next phase will be defined by what the data show, or fail to show. Until then, the distinction between proof and speculation rests on a handful of upcoming observations. The scientific community waits, knowing that each new measurement could tip the balance between the extraordinary and the explainable. On October 3, 2025, Mars orbiters captured confirmed images of 3I/Atlas traveling at 60,000 kilometers per second, far faster than any known comet of its size. This third interstellar object exhibits at least 7 documented anomalies, including an oversized mass, nickel-rich plumes, a trajectory closely aligned with the ecliptic, and a rare anti-tail. Harvard scientist Avi Loeb, citing these facts, assigns a 30 to 40% chance that 3I/Atlas is not a natural object, but stresses that this assessment relies on current but incomplete data. Major agencies like NASA have yet to release key observations due to the government shutdown, and critical imaging from Mars Express and the European Space Agency's JUICE mission is still pending. While Oumuamua and Tupouniai/Borisov sparked debate, 3I/Atlas has escalated the scientific stakes. The evidence leaves experts divided and the public waiting. For now, the true nature of 3I/Atlas remains unconfirmed. The next wave of data will determine whether this visitor is a natural wanderer or something entirely unprecedented.